Good day, ma'am. Shall we start the session?
Wait. Sir has joined, Professor Senthil Kumar. Happy afternoon, everybody. We'll start the meeting as soon as our resource person has joined.
Madam, Sandeep had joined.
Yeah. Good afternoon, sir.
Welcome, sir. Welcome, sir.
Dear participants, kindly mute. Dear participants, kindly mute.
We'll start. Shall we start? Yegamai?
Yes, ma'am. Good day, ma'am. Good day, sir. Prayer. Am I audible, ma'am?
Yes. Let us start
Prayer.
with Tamil Thai Valthu.
நம்ம குரூப்ல போட்டேன் லிங்க் அனுப்பவா?
Good afternoon, one and all present here. Knowledge alone is not power. The sharing of our knowledge is when knowledge becomes powerful. Quoted by Rich Simmons. Once again, good afternoon, one and all present here. It is a moment of extreme pleasure to welcome you all who are present here to attend this UGC HRDC National Webinar on Machine Learning. The session 1 was followed by Convolution Neural Network Architecture for Medical Image Classification and Segmentation, and followed by session 2, hands-on order of examples of selected architecture, VGGNet, ResNet, AlexNet. I welcome Dr. P.L. Chitra, Madam, to propose the welcome address.
மேம் அன்மியூட் பண்ணுங்க மேம். பேச கேட்டா சித்தா மேம் அன்மியூட் பண்ணுங்க.
Happy afternoon, everybody.
Yeah.
Respected Director, Professor Dr. Madheshwaran, Deputy Director Dr. N. Kodandaraman, dear colleagues, Dr. M. Sornam and Dr. B. Lavanya, professors from our own university, other universities, government college professors across the country, young research scholars, ladies and gentlemen. A warm and heartfelt welcome to you one and all present here. Happy to connect with you again through UGC HRDC sponsored national webinar on machine learning. Learning gives creativity. Creativity leads to thinking. Thinking provides knowledge. Knowledge makes you great. Said by Dr. Abdul Kalam ji. This is particularly true in our machine learning field, right? So we want to impart intelligence to the machines, and we want to make our system to learn, and we want to impart knowledge to the system. So this webinar has been brought on today, specifically on Saturday, for the benefit of the most of the faculties, research scholars to update knowledge on this domain of the session 1 as convolutional neural network structure for medical image classification and segmentation. Followed by session 2, which will focus on hands-on art of examples of selected architectures, VGG Net 32, ResNet 3050, DenseNet, etc. by our eminent and potential speaker of the day, Dr. T. Sendil Kumar, Associate Professor, Computer Science and Engineering, Amrita School of Engineering, Coimbatore. Hearty welcome you too, sir. Listen
Thank you, Chitra.
and observe the webinar to enhance the knowledge in this research domain. Once again, on behalf of the Department of Computer Science, University of Madras, I welcome you one and all present here. Thank you.
Thank you, Chitra. It gives me immense pleasure to introduce our today's speaker. I'm profoundly delighted to take an opportunity to introduce the speaker for the day, Dr. T. Sendil Kumar, Associate Professor, Department of Computer Science and Engineering at Amrita School of Engineering, Coimbatore. He completed his B.Tech Computer Science and Engineering from Sedu Institute of Technology, Madurai. He completed his M.Tech Distributed Computing Systems from Pondicherry Engineering College. Sir completed his PhD in Information and Communication Engineering from Anna University, Chennai. He has received appreciations in Indian Express for agent-based programming for banking domain. He has published 9 national conferences, 14 international journals, and 10 edited book volumes. Sir has 22 Scopus publications and also published a book on C++. He is a reviewer for Elsewhere, Computers and Electrical Engineering Journal. His research interests include video analytics, big data analytics, machine learning for big data, intrusion detection system, and so on. I'm so happy to welcome you, sir. So, our honorable speaker, please start the session.
Thank you to Chitra ma'am, and thanks to the team for getting the stage for the session. So we'll start with the session. So I'll first share the screen. So the plan for the session is we would start with CNN for medical image segmentation. So that's the first part of the discussion. We will come down to architectures which are developed exclusively for enhanced learning of data. So there we will look at ResNet, and we will also look at other architectures like AlexNet and see how it can be applied for image processing. Right, so that's the plan for the session. I've shared the screen. I think people should have seen the screen too. Now, when you set the understanding of problems, especially with respect to medical imaging, the first input everyone should have is like the data that you actually process always.
Sir.
The image has.
Sir, your voice is not clear, sir.
Am I audible? Am I audible?
Your voice is not clear, sir.
Okay, 1 second. So now is it clear? Hello? Hello?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay, thank you. Thank you. See, when we look at medical images, first thing that we should understand is like the medical images have very important challenge of varying gray pixel levels, right? When you take a color image, it's very easy to process because the varying colors are falling into the ranges correctly. But when you look at a medical image, the varying pixel colors, especially the gray levels, are very challenging, right? And second thing we should always keep it to understanding is what is the medical image data set that you're going to work. This is a common information for all the researchers and project doing students, whether you are looking at possibly of brain tumor images or you are looking at images with respect to retinopathy. What is the nature of data set that you're going to work is very important. because there people will talk to you saying that we are looking at DICOM images or we are looking at MRI, CT scan images and so on. This is second input you should always understand. The third constraint is like today in medical imaging, there are a lot of possibilities for you to do multimodal image processing. For example, earlier days we
Dr. N.G. Ramachandran Sir, put in slideshow mode. Next train to mute it.
Yeah, okay, fine. So third
slideshow mode, sir. Please put on slideshow mode, sir.
Yeah. Third thing here is like when you look at a medical image, there is a lot of possibilities for you to do a multimodal image processing. For example, like now we have got devices which can actually do two images formats together and do a processing. For example, if you have MRI and CT together, still we have systems that can recognize information from both the type of images. So these are all the piece of information that I am leaving it to all the participants before I start the session. The medical image is different from other images because there are varying gray pixel levels. So the varying gray pixel levels is going to be very important to understand what type of data you want to understand from the medical image. The second important thing is the type of medical image that you're going to work with, whether it is an MRI, CT, like that. The third in importance is like, is it possible to work on multimodal image data set? Now, the next we are looking at the session perspective is we are looking at how CNN can be taken for medical imaging, especially for image segmentation, right? So, if you look at CNN, a quick thought would be like CNN stands for Convolutional Neural Network, and CNN can actually look at an input image very nicely. For example, if you look at a CNN here, left side what you see is a 2D structure of an input image, and the right side what you see is actually values with respect to the medical image here. Here we can actually take the use of the layers which you have in a convolutional neural network. Normally in convolutional neural network you will have one or more convolution layers, and you can actually have a pooling layer also together to predict the type of image sets. Now, why people have looked at convolutional neural network when there are other architectures that are there? Suppose you take an image of size 200 cross 200 cross 3, right? And it means that you're looking at 3 color components. So in this case, if you have a single fully connected neuron in the first hidden layer of the neural network, you will get 200 cross 200, right, cross 3, which will give you around 1,20,000 weights, right? Now, if you're going to take the case of a CNN here, what is possible in the case of CNN would be like the neurons in one layer will be connected to only a small region of the other layers, right? So there, what you can do is you are trying to use your CNN more better, and the number of dimensions in the neural network also gets reduced. So that's the first point that people should understand. We are going for convolutional neural network because we are able to achieve dimensional reduction, especially on the data set that you are using, right? So it means that if you have an image which is into the class that you want to consider, then the images that you have can be classified into all possible set of n classes. How are you able to classify is you are able to classify using the depth as a dimension here. So left side what you see is a comparison between an MLP versus a convolutional neural network. If you take a multi-layer perceptron here, you can see layers and an input, you have hidden and you have output. Now you take a CNN, it will look like this. Now in a CNN, you can see that the interconnections as such will be partially being provided, right? This is a partially connected CNN. That means this 2 alone is connected to this neuron, this 2 is connected to this neuron, this 2 is connected to this neuron at the hidden layer. So this is the difference between an MLP versus a CNN. Now if you go further and start asking as a regular neural network, which all of us know, if you take a 3-layer neural network, you would say you have an input layer with 2 hidden layers and an output layer like this. This is a 3-layer, right, neural network. Now, when you come to the case of a convolutional neural network, what it does is it arranges its data, especially in terms of neurons, in 3 dimensions. One dimension would be the width, the next dimension would be the height, and third dimension would be the depth. So here you can see, whatever data that you have provided, it is kept as in terms of width, height, and next is depth here. So if you take a medical image, it's also same. It will try to arrange its neurons based on the data that you have provided in form of depth, height, and third is going to be width here. So how does the convolutional neural network works? It actually takes a set of pixel values that you're providing, and once you're giving to a convolutional neural network, it will try to either say it is falling into a pattern of X or it's falling into a pattern of Y. So what does this X and Y would look like? If you take an image which you say that it's going to classify it as X, it would have a pattern like this. Now, if you look at this case, now the major advantage of going for a CNN is any input that you provide can actually have some sort of operations. For example, somebody who is writing an X would rotate the value of X and keep, right? Somebody who is trying to write a value of X would write smaller, right? So ideally, any image that you take would undergo operations like translation, scaling, rotation, and next is weight, right? Now, if you take images, which is again X, as what I told you, right? This image of X, if I'm going to undergo a translation or a scaling or a rotation, or it's going to change in terms of weight, as you can see here, no? There again, a CNN will still recognize it as X. Same case with respect to O also. Now, if you look at X and O, it looks as very simple for you because you would assume it as alphabets. But if you take in terms of a medical image, and let's take this as something with respect to the human body organ, then if that human image, especially with respect to the organ, has undergone a translation or a scaling or a rotation or a weight, change in weight, still my CNN will recognize what is the nature of the image, right? So it means that a CNN can actually look at all possible cases of classifying the data. That's the input that I'm trying to see here. Now, let's see how a convolutional neural network is taking in terms of your understanding with respect to a computer. Now, if you take it in terms of the computer here, this is left side what you see is the image, right? Where this is in pattern of X. The right side what you see is how the computer assumes it here. Now, if you look at how the computer is going to assume here, the computer as such will assume the set of values to be equivalent to the varying set of gray levels, and then it will process the data, right? So in this case, if you look at this example, that you have a pattern where it is not exactly matching as X, so the computer will not say that it is an X here, right? So now comes the next question of asking, like, if convolution layer is available, what are the other layers that are there with respect to CNN? The other layers are, one is going to be an layer. So what is really going to do is it's going to have an activation function. The activation function will try to apply a thresholding, which is a max-based thresholding, that is max of 0, X, right? So next is a pooling layer. What a pooling layer is supposed to do is, it is supposed to do a downsampling on the data along the two parameters. One is called as a width and next is the height. So what is the width and height? We just now told you here. You give any data, your convolution neural network will take the data in terms of 3 dimensions. One is height, width, and next is depth. Okay, 1 second. Okay, yeah. So together with the convolution layer, we have other layers as we have told you right now. We have pooling layer, we have fully connected layer also being available. Yes, okay. So what a fully connected layer is supposed to do is, it is supposed to give you the class scores, right? Equivalently saying, if I give a test image, it will try to say the score value corresponding to the set of classes with which you have trained. So this class value is n, right? So you are trained with n classes. It will say what is the class score for the test data as matching to n of the n classes that you have taken, right? So this is how your layers looks like. Now let's go back to the previous example and see here. In the previous example, what we have told you is, if we give a pattern like this will not match because it's not in the same pattern of X as you see on the right side. Now, if you look at this here, you can still see that if you look at this one, this looks as X, right? Now, let's understand with respect to this pattern here. Now here, if you look at this, what has got changed, right? The convolution layers is very interesting because they will be able to identify the patterns instead of just pixels. Please understand, participants. Instead of taking it as pixels, now the convolution layer has a strength saying that it can match the patterns. For example, if you look at the left side image and the right side image.
Excuse me, sir. Some background noise is there, sir, along with your foreground voice.
1 second.
I request all the participants unmute your mic.
Ma'am, now is it okay? Hello? Madam, is it okay now?
Yes, sir, we will see, sir. Please proceed, sir.
Okay, fine. So what a CNN is capable of is it will be able to see the patterns, right, rather than looking at pixels. As you can see here, the left side image, we have one pattern. It looks for a similar pattern on the right side image. Same here, it looks for a pattern like this in the right side image. So that's the strength of convolution layer, right? So first information to people is, now if I look at this as a medical image, if medical image is going to have some patterns, whatever pattern is there in the left side of the image, the same pattern I'll be able to look in the right side of the image also when I compare. Okay. Now, a convolution layer has got some filters, so it means that using filters, it can actually learn all possible information which is there in the image, which is there in the test part, with the corresponding images with which it has, right? Now, when you try to convolve, what you are trying to do is your filter as such that you have designed will try to do a dot product. So possible set of filters are provided here, filter 1, filter 2, and next is filter 3. Now sliding the filter over the width of the image and the height of the input will actually give you something called as an activation map. The reason is, like, you are actually trying to do a dot product of the filter over the image. Suppose you take this filter, I am trying to superimpose on this image region and I am trying to see. So what I will be getting is something called as an activation map here. Same way, I can take this filter and try to place it anywhere in the image. Now what you have seen and what you have concluded to your learning is, you can understand that, okay, if I have patterns, the patterns can be recognized by using the concept of CNN with a convolution layer, right? Now the next question would be what you can do with respect to the stride. So stride, generally what we will say theoretically is, we will say that how much number of pixels we want to shift during every convolution operation, that can be decided by using the stride, right? The same way, if you want to differently what a stride would be, is you can say that it is a distance that the filter is moved across the input from the previous layer, right, during each activation. It is also referred to as slide. Now look at this here, it is a one-way convolution, right? Here filter is 1, filter size is 2, right? Filter is 1 and filter size here is 2 here. Now when you come to the right side that you see here, you can see that it's a one-way convolution. Filter is 1, filter size is 2, but here stride is 1 here. But on the left side, you can see that the stride value will be 2 here, because here the filter is moved 2 positions during every convolution operation here. Now, the next that needs to be understood is about padding, right? As far as padding is concerned, the importance of padding is like when you have an image which is not a square matrix, you can convert it to a square matrix by doing a padding, right? So what you do in a padding is you actually try to fill it with zeros. So if you look at this operation here, left side you can see a 1D convolution that you want to do on the given input, right? And you have filters as 1, filter size as 2, and you have stride as 2, and padding is 1. Right side, you can see padding as 2. Where do you see the change of padding as 2 here? You can see here, right? It will reflect in the hidden layer part. So you have 2 padding operations, so padding equal to 1 and padding equal to 2. So padding as such will allow you to fill the values in the borders with zeros, right? Now what you have learned is with respect to convolution, you have learned with respect to padding and stride. Now let's walk through an example to understand how it happens. Now this is the input image for our example. Stride is 1, filter size is 3 cross 3 by 1, right? And padding is 0 here. Now when I try to do a convolution operation, I take the filter and place it over the region here. So it is a dot product operation, right? Now next step what I do is I take the same filter and I try to place it in the next 3 cross 3. This keeps going until I reach the end of the image. I think people can see very clearly. So I move next, I reach the end of it. Now what happens every time? So what happens every time is it is a dot product operation here. So what would be a dot product operation here? Suppose you take this, the value of the filter is 1, the value of the image is 1. So you say 1 cross 1 is equal to 1 here, right? Now when you continue doing, you will take the next pixel values also which you have in the image and you will try to do a dot product with the filter values. So now this gets filled. So what you are doing here is you are taking the next, that is -1, you are multiplying with this. It will be 1. Same way, you take -1, you multiply with this, it is +1. So next, you take -1, multiply with this, you get 1. Next, you take 1, multiply with this, you get 1. Next, you take -1, multiply with -1, you get 1 here. And last two is same, you take the values and multiply with the pixel values in the image, you will get a resultant value which will be the activation map value. Fine. Now, once you have done it, it means that your filter is applied on the image, you have a resultant image in front of you. Now, when you look at this, the resultant value that you provide would be the sum of the values that you got divided by the total number of pixel values that you considered. It is 9. Madam, I think somebody's audio is on. Okay. So it is divided by 9. You will get it as 1.
So all the participants are requested to unmute your mic. Cooperate with us. Sumitra Subramanian, please unmute it. Okay, fine, sir.
Okay, fine. So once your filter operation is applied, you get 9. So it is 9 divided by 9 will be as 1. So that becomes a value here. Right. So, okay. Now this goes for the rest of the image pixel values also. Now in this case, what happens is after you do the multiplication, the resultant values is this. You sum up the values. It is a value which is 0.55 after dividing the numerator by 9. So the value that you get here is 0.55, right? Now this is how your final set of images will look like. I think people should get a picture very clearly. So the input image is like this, which is a 9x9 image. So input size is 9, filter size is 3x3, stride is 1, and the filters is 1 filter. Padding, you are not doing any padding here, right? So the padding value is 0. After doing the filter operation over the image, that means you take this filter, take it on first 3x3, next 3x3, like that. As you continue your operations, you will get a resultant set of pixels like this. Now comes the question of asking what will be there in the feature map. So the formula is 1 plus W minus F plus 2P divided by S. So if you take W, right, so the value of W is 9, right, and you have F is nothing but a filter size, so it is 3 cross 3, it is F is 3. Then 2 into P is nothing but padding. Here you are not doing any padding, it will be 0. Stride, you are moving 1 pixel right. So S is nothing but 1. Once you apply on this formula, you will get a value as 7. So the feature map size is 7. So as you can see here, it is 7 cross 7. So given an input image of size 9 cross 9, the feature map that we are getting as an output is 7 cross 7. Now, if you look at this here, for one convolution, right, if you have filters as 3, right, it's not one filter, you have 3 filters as you can see, filter 1, filter 2, filter 3. Okay, and please understand each filters are different. If you look at the values of the filters, each filters are different, right? So once you apply like this, again when you take it to the formula here, right, which you have seen 1 minus W minus F plus 2P divided by S, right, you will get an answer as 7 cross 7. But here only change would be it is 3 because the number of filters that you applied is 3 here. So the output of convolution here will be given as 7 cross 7 cross 3. Now, if you take a convolution layer output with respect to what we have seen now, you get values from filter 1, filter 2, filter 3. So that's what you can see here, filter 1, filter 2, filter 3. Now, it is a understanding to all the people that you can actually use convolution layer more than one also, right? That means at every convolution layer, you can actually use a filter that you want. Now comes the next question of the activation function. There are many activation functions available, and when you come to CNN, we have ReLU, which is a very popular activation function. Now let's see what ReLU can do. Now if you take the feature map value that you got from here, you can see here one of the first pixel value here is 0.77. Next is 0.11. So what does a ReLU does? So ReLU as such, what it does is it takes the values and then it applies its function and then gives an output. Now the same thing happens for all, right? Now universally, if you look at what a ReLU can do here is all values which are negative, you can see here, no, minus 0.11, minus 0.11, minus 0.11, minus 0.33, everything has become 0. So that's what a ReLU does actually. So it takes the values that just come as an output in the feature map and looks for all the negative values. Wherever it is negative, it will try to convert it and keep it as 0, right? So a stack of images that you have provided right now, after giving to a layer, right? So what it does, a ReLU layer as such will try to give images with no negative values. So if I take my first image that I get from the filter 1, all negative values have been removed and they become 0. All negative values from the second image, that means after applying filter 2, its values have become 0. Now it is available here, right? 1 second. Now stack of images that you have originally right now has become stack of images with no negative value because you have applied a ReLU activation function. So that's the importance of going for ReLU, and ReLU is an activation function which is default used in the case of CNN. Now the last one is a pooling layer. So what a pooling layer will do is a pooling layer will actually downsample the values that you got in the previous layers. So its function is very simple. It has to reduce the spatial size of the input image, right? And when you reduce the spatial size of the input image, automatically the amount of computation that you perform will be getting reduced. So that's the reason we go for a pooling. And pooling as such is more important when you go for high dimensional images. You talk about medical images especially, they are of high dimension in nature. Now what is a pooling does is like this. If you have a pooling filter size, okay, which is 2 cross 2 and its stride is going to be 2, that means it takes 2 cross 2 here, right? So it takes 2 cross 2 every time and it takes a maximum out of it and places. So this is 1, right? Now similarly next to 2 cross 2, the maximum value here is 0.33 because 1 is 0.11, next is 0.3. The same here 0.5 and so on. So as you repeat the max pooling that you have done with filter size of 2 cross 2 will give the maximum values of every 2 cross 2 that you have taken. So the resultant of applying a ReLU function will give an image like this, and after that you are trying to do a pooling will give you a resultant image like this, right? So this is how actually pooling works. Now, if you're going to take larger images, right? So for every larger image that you have taken, after applying a pooling, you will get smaller images like this. So in a way, what you have achieved is you have reduced the size of the image. So the computation that you're going to perform on the image here will be less compared to the computation that you would have performed on this image. So that's the purpose of what a pooling does. Now, you look at the bigger picture of what a CNN says. A CNN says that you give an image, I will give it to the convolution, and then I will give it to a ReLU, right? We have seen what ReLU does. Then I give it to the pooling. Then finally what I do is like I will be able to get equivalently output images like this. Okay, this is what actually CNN does. Now, if you look at the convolution part, right, more in detail, you can always say that I can actually convolve with any number of filters. For example, if I want to convolve with 64 filters, then pooling also here I will specify it as saying it is 112 cross 112 cross 64. The reason is when I'm doing a convolution, then I'm doing it to a pooling, I assume that it is reduced by half. So it means 224 divided by 2 would be 112. 224 divided by 2 would be 112. So I get it as 112 by 112 by 64. So that will be my output from a pooling. So now if you look at an architecture that you create, then people will say that I have convolution, ReLU, right? Then I have convolution, ReLU, then I give it to a pooling. That means a stack of convolution and ReLU layers, right, would be followed by a pooling. So please make this point, participants. You can have stacking of convolution and ReLU, and you can give it to pooling. So here I say convol, then apply ReLU. Then I say convol, again apply ReLU, then I give it to pooling. Somebody might say, why you want to give it here? Maybe you can give one more convolution and ReLU and give it to pooling. Yes, that's also okay. So how do you decide this? So people will ask how many convolution layers, how many pooling layers should I use? So there's no direct answer for it. One is you actually create your model by specifying the parameters from the research papers. For example, if you have taken a research paper and that research paper says very clearly that use 2 convolution layer and 1 ReLU. So it is giving you good results for the medical imaging. Please use it, right? So there is no direct answers for it. But the other clarification that you can always assume would be like the loss that you get after you run the model, right? So the loss should be minimal. If the loss is high, it means that you have to go back and fine tune the model. So that's how we say that when you go for deep learning, especially in the case starting with the CNN, we are trying to stack the layers deeper. So that means as you go 1, 2, 3, we are going to stack the layers more and more. So you call this a deep stacking, right? So last one is actually the fully connected layer. So what is fully connected layer is they actually take a normal set of flat values and provide. For example, if you have a output like this here, so the values are 1.55, 0.55 and 1, right? So which you are getting. So what actually a fully connected layer will do is we'll just try to have a normal flat operation. So it will say it is 1, 0.55, 0.55 and 1 here. So here it will try to stack the values and keep it. So last stage when you try to come up, what we'll do is we'll try to rearrange the output matrices. The output array, which is a one-dimensional array as you can see here. People will try to ask a question, what sort of an activity is available to predict the classes? We generally have a non-linear activation function, softmax activation function for the problem. If you have a summation of inputs, right, and weights at each, you can actually predict what is a pattern that you have, whether the pattern is either X or whether the pattern is either O. So this is a two-class problem. To all the people, it is actually a two-class problem that you are looking. Now the same X and O, somebody would say it is X, I, O. Then in that case, it becomes a three-class problem, right? Now putting it all together, our summary of learning from the discussion here is, I give an input image which is actually having some values. I will apply it on the filter. I will actually do a dot product on it. I have a convolved image, right? And then when I give it to ReLU, what happens is where it's making it as, so combination of convolution and ReLU layer can be as a stack. Then I can give it to a, so pooling will try to take every 2 cross 2, give the maximum out of it, and finally I'll get an output which I can give it to a fully connected layer. So your architecture can have stacking of convolution and ReLU, and you can give it to pooling, and you can intermediately take the output, again give it to a stacked layer like this, and then give it to a fully connected layer. Now comes the question of the hyperparameters that you're going to provide in terms of your CNN. So the hyperparameters that you provide means it's a set of values that are fixed by the model. It's a set of values that are fixed by the user. That means you are providing certain values as part of the model itself. It's called as hyperparameters. So example is like filter size, number of parameters, padding, stride, all that is hyperparameters which comes under convolution. When you come to pooling, you can give the window size, because in this case what we have discussed, we said that we are trying to use a size of 2 cross 2. But this is not a very standard size always. Sometimes people will look at architectures where the filter size is larger. It's not 2 cross 2 here. So that is also possible. So the window size can be adaptive window size also, which comes under hyperparameter. Stride, as I told you, is the number of rows that you move every time you do the convolution operation. So that's also hyperparameter. And when you come to fully connected, you are looking at the number of neurons that you're going to have in the fully connected layer. So all these are examples of hyperparameters in the model. So now the first part, what we have seen is about the theoretical aspect of how CNN works, right? Now what we will do is like we will start looking at the coding part here of how CNN works here. One second. So I will first share URL. So we will try doing the code on Google Colab. So request all the participants to open Google Colab. Am I audible?
Yes, sir. Yes, sir. You are audible.
Okay, fine. So I am taking an online.
Audible, sir.
Yeah, okay, thank you. I'm taking an online resource which is available for medical image processing. 1 minute, I will. Yes. I'll share the screen. Okay. I think participants can see this. I will also put it in the chat box. Don't worry. So here, yeah, this is a GitHub that I'm posting for reference. Okay. So if you see this GitHub, actually this is talking about medical image segmentation with convolution neural network. So here they look at many things. First is they look at 2D or 3D medical image segmentation for binary and multi-class problem. And here there is already a library called as MIS-CNN. Okay, this also people should understand. For most of the regular things that happens at the research level, proprietary architectures come up. So there's already a library called as MIS-CNN, right? Especially for medical imaging with convolution neural network, which supports many things like this. One is segmentation, then it supports metrics, then it supports prediction, cross-validation, right? And it is based on Keras with TensorFlow. In terms of deep learning, it's based on Keras with TensorFlow. So this is a diagram actually with respect to MIS-CNN, and as you expand, you can actually see the different characteristics, pre-processing, data augmentation, all that will come here. Now, when you look at this next step, right? Next step is like in terms of the coding part, right? You need some libraries and then you have to start working. Now, how the code looks like less, like you need first a library. So the library is MIS-CNN. And the next step is like you are trying to create a data interface for learning. So here they are looking at kidney tumor scans, right, which is available as NIFTI format, right. So here they actually import NIFTI underscore interface, right. The next is the data set part. So here they are using this data set available. So you take this and put it to the browser. Yeah, you take this and put it to the browser. It will try to access to the URL. 1 second. That's a URL from the GitHub page. Yes. Yeah, you can see the yes dataset URL. Now, when you go back to this here, you try to take the data instance from this URL here, and then next what it does is like they are trying to configure how the data can connect to the patches, right? For that, they are trying to use a method which is available already, which is called as preprocessor method, right? Then next what they are trying to do is they are trying to import architecture. Here they are trying to use a unit architecture, right, together with CNN, right? Now, as you come down, next step what they do is like they do a training part. So here they are looking at 80-20. That means 80% for training and 20% they want to look for testing, right? So this is for the training code. We already know we have to use a object called as model. So dot method name is train. So here you say 80, and next when it comes to training, they're trying to look at 20 samples for prediction. So it is 80, 100. Then next what they do is they run through a classification part. So it is a 5-fold classification that they want to do. So here they actually call cross underscore validation, which is actually a package. Then they call this method called cross underscore validation. They specify the number of folds to be 5 because they want to do a 5-fold classification. The number of epochs they mention is here is 100 here. Now if you want to run this code, you need to install this library, which is MISCNN, that I'll show you also how to do it in the Google Colab. As you run this, what happens is this takes the data set which is there in the kidney tumor segmentation challenge, which is posted in KITS 19, right? So that's what you can see here also. Yeah. You can just see here. So this takes a data set which is posted in this URL, right? So it takes a data set which is posted in the URL, and then it tries to show the output. So again, as we see here, everything is an image, right? What they are taken here. So the image is being trained, and then they do a prediction here. As you come down, they are looking for all the individual cases at every slice. Okay, so when you look at the slicing, it is actually slicing of 100 maximum. So it runs for every case, all slice values till maximum of 100, right? For that, what they do is they actually try to do and show you the ground truth data. This is your ground truth data that is there, and this is prediction. So it looks like something animated because it is taking every slice, right? One slice is equivalent to one image that you consider. So it's taking all slices, slice 1 to 100, and for every slice, it is trying to show you the prediction part. Okay. This is this is a very good example for people to try. Now coming to the GitHub part, right? Coming to the GitHub part. Now, if you go to your Google Colab, right? This is your Google Colab link that you've taken. So I think people have opened Google Colab. So this is the command that you are supposed to use for installing the library. So library that you want to install is MISCNN. So this will be the syntax. So pip install MISCNN. So I just put it in the chat box. So this is a general command. Whichever library you want to install, no? Let's take a library name as XYZ. You will say pip install XYZ. Automatically it will get installed. So I've done it here. So now what it does is it's trying to connect and it is trying to install. So I will post the same in the chat box for people to do. Getting it in the chat box. So if you're getting it, what you can do is you can go to your Google Colab. Everybody is conversant, right? So you have a email ID in Google Colab. So when you go to Google Colab, you log in with your Gmail ID. It will ask you for a Gmail ID. So I have logged in with a Gmail ID. So it gets an environment like this. So here you go and click this option of plus code. That means you will get a code where you can start typing. So let's take this as a code I want to paste. Go here and paste. And I will have a button here on the left side, which is for running the cell. If I go and click this, it will try to run and it will install the library. The library here is MISCNN. Okay. Once you have done that, then the next step is going to be from what we have shown you here. So next step would be like you can go to the GitHub. So here you can see here there will be a code, right? And this code as such you can copy and you can paste it. Okay, this code you can just copy. Once you move the cursor here, no, you will get a button. Yeah, you will get a button here for copying. So you can just go here, copy. So you can copy the code and you can paste it. It will run. And once you've done it, you can take this code and you can paste it. Again here, okay. Once you select this, you get the code. Once you have done it, then next step is you have to run this code. Once you run this, then automatically you will get an output like this, where it will show you the performance graphs with respect to the loss. So right, and equivalently below, it will try to show you the ground truth data. So this is the first code which I feel is more close to image segmentation, which participants can try at your desk. Okay. Any clarifications at this point? Participants, any clarifications? Now what we are doing with this CNN and image segmentation with CNN, medical imaging. Am I audible? Participants, any clarifications from your side?
Sir, one question is that
Yes, please, sir.
if any numerical is asked regarding the number of filter or filter size, how we can calculate that thing?
Okay, fine, sir. You are actually using, you will generally use filters of size 2x2 or 3x3, right? Ideally, a filter that you would take would be 3x3. Because for a binary, because if you go for a 2x2, then you will have a binarized operation that will not give good results. So you would ideally use a filter of class 3x3. And again, all these filters are proprietary filters that you have learned in image processing, median filters, Gaussian filters, like that. So you can choose any filter that you want, and the only thing is you are trying to apply the filter here.
Okay, sir. Okay, sir. Thank you.
Have I answered your question, sir? You're clear with my answer? Hello?
Yes, sir. Hello?
Sir, are you clear with my answer?
No, answer is okay. Actually, sir, I have found some problems, numerical problems regarding that they have asked that what will be the number of filters and other things. I was not unable to calculate that thing.
No, can you repeat your question? Repeat your question. What is your data set?
Actually, this time I don't have, but so many questions are asked. Actually, I'm asking the general type question. Is if anyone is asking in a problem way that how many filter is used in that.
Okay, sir. Okay, your question is like how many filters should I use with CNN architecture? That's your question, sir.
Yeah, yes, sir. Yes, sir.
Okay. I will give you an answer in another way, sir. Ideally, when you choose a filter, you are trying to improve something from the given image, right? Because you are using filters to improve the information in the given image, right? And when you look at filters, you have filters which are basically at pixel level. You have pixels, you have edge-based filters, you have region-based filters. Sir, am I clear? Hello?
Yes, yes, yes.
Yeah. So now if you have an image in front of you, and that image is actually looking at enhancing the pixels, which are closed regions, you will actually choose filters which are suitable for region-based. Right? Yeah, so that should be the way you can put your answer, sir. Based on the image and based on what you want to enhance from the image, you look at the choice of filters. For example, I want to extract one, I want to improve one edge, right? And I want to improve one region in the given image. I will look at one edge-based filter and one region-based filter.
Okay, okay.
Is it now clear, sir?
Yeah, yes, yes. Thank you, sir.
Yeah, thank you, sir. Thank you. Any other questions from the participants? Okay. So that's a big canvas. I believe people are able to understand. Are you able to understand? Please at least type an yes in the chat box, please. Participants, please acknowledge. Can you give at least an yes in the chat box? Yeah, fine. Okay.
Sir, by installing, I have a doubt, sir. By
Yes.
installing the PIB MISCNN, it's giving me a warning like the following packages were previously imported in this runtime. So you must restart the runtime in order to
Correct, ma'am.
use.
Button yes. It will get restarted and the session will become active. That means you are just trying to invoke an instance on the Google Colab, right? So it's like a session. So in that session, you want to configure this MISCNN. Once you exit from now, again it might ask you to restart the session.
Okay, sir.
Okay,
I
okay.
have given yes.
Yes.
Okay, sir.
Yeah, correct, ma'am. Correct. If you given yes, it's fine. Okay.
Thank you, sir.
Yeah, thank you. Okay. We will move on to the next part. See, when CNNs are more suitable for medical imaging, then comes the next question. What are the other architectures that you can use and how the architectures are more suitable to the problem? Right? There are many architectures that are there. So you can actually conclude always that if you take CNN do not have the capability of remembering. That means it will not go back to the previous data and compare whether the architecture is learning from the previous layer or not. So the previous layer learnings are not seen in the case of CNN. So people started asking what can be the other architectures that you can choose which can actually be more suitable to the problem. So there people talked about architectures exclusively, like one architecture is people talk about RNN. People talk about architectures especially with respect to ResNet, right? People talk about architectures like GRU and so on. So the next discussion that we're going to see here is actually going to talk to you asking like what are the other architectures that you would like to work?
There are, sir, excuse me, sir. There are two questions.
Yes, ma'am.
The chat box. I think one Dr. D. Jagadishan has got an error. It is being posted in the chat box. Another one from query from Karthik M. Is it possible to fix filters in each layers manually? He was asking.
Yes, sir. You are only see when you hard code, no, you are only giving the number of layers, sir. The number of layers is not provided by the model. So that is why you call it as a hyperparameter. Hyperparameter means anything that you are trying to provide. So you can say number of convolution layers is 2, number of pooling layers is 1. But if you have a question, how do I fix the number of convolution layers? Is there any theory? Industry level practice also, the answer is like you go and check for the amount of loss. When the loss is minimal, you can conclude that the hyperparameters that you have fixed is correct. You are including the number of layers. Or you can actually go to the concept of hyperparameter tuning. Right? There is a separate area called as hyperparameter tuning, where people talk about how hyperparameters can be tuned for any problem. So if you take such things, what happens is like your hyperparameters are tuned. So you are able to fix your hyperparameters based on the objective function that you decide. If the objective function that you decide is saying a loss has to be around 0.6 to 0.7, based on that, it will itself give you a possible set of hyperparameters. So that is the answer to you, sir. Are you clear with my answer, please? Can you acknowledge in the chat box? Hello? Yeah, okay. Then I think, sir, are you acknowledging? Okay. The other error, I think it's a, you are asking like you should restart. Yes, sir, please restart. The session will restart, but don't worry, it will restart means it means that your next set of code you can copy and paste it. Okay. That's the answer to Jagadishan, sir. Okay. Now, madam, shall I go next?
Yes, sir. Yes, sir. Please.
Fine. Okay. Now, next, what we will look into is the other architectures and the substance of learning from there. And please understand, when we are moving to architectures now, this is slightly in a more abstract manner, right? We will not go and look at the piecewise steps like what we have been trying to do. Till now, we have been saying that step 1, this happens, step 2, this happens, and so on, right? And before going into that, I want to show you this slide. This is just for your information. All these architectures are based on neural network, right? And ideally, it is a perceptron that we are using from neural network. So the Mark 1 perceptron machine was the first one to have the implementation of perceptron algorithm. And it,
slideshow, sir.
Yes. And it is back in 1957, actually. So this is machine as such was connected to a camera that used a 20x20 cadmium sulfide photocells to show a 400 pixel image. Now we are just seeing it in computers like simple steps happening to show some images output. Right side is actually the display of the image which they have presented. And this is back in 1957. You know where we are right now. So this has been the small history behind the neural network. And second is actually the contribution from these two people, which is Adelin and Madeline, right, back in 1960. They were the people who were able to try to conclude saying that we can have a quantizer to regulate the output in neural network. And third is this theory of back propagation, because if this is not there, right, we will not have even deep learning concepts. Reason is, in deep learning we say that every time we do a back propagation and we find the weights that are participating in the learning, right? So this is possible because there was back propagation concept, and this goes back to 1986. Okay, and this is a first step in deep learning, which started back in 2006. Okay, if somebody has a doubt where did we start with deep learning, which year it was, it's 2006. So where they started saying that you can have stack of layers and you can do a prediction here. This I just want you to see so that you get an idea of closer to the history of deep learning concepts. Now let's move on to the next one. So the next architecture we will step into is VGGNet. Okay, so the next architecture we will step into is VGGNet. This architecture is very popular because people say that this architecture is suitable for many type of problems. And before we step into this architecture, we should know that there is something called as stochastic gradient descent concept, right? So what do we do in this stochastic gradient descent concept is like we iteratively train the input data and we try to minimize the loss, and every time the gradient will be minimized. So if you have the derivatives in general, ideal derivatives that you will have is a partial derivative, or you will have a total derivative like this. Okay, so here when you look at the derivatives will try to optimize the maximum information that you will try to have from the input data. Leave the mathematics here. Ideally, we are trying to talk about the importance of the concepts. So here, what is being suggested is like we can use a Jacobian operator. So the Jacobian operator here is nothing but a matrix. So and it will be of dimensions n cross n. So this will have suffixes n suffix in and n suffix n out. That means it is input and next is output. So if you have a scalar loss, the last Jacobian that you would get here would be like this, where you would say it is product of I suffix f, then you have j suffix j, and next is j suffix h here of z, right? And this is the reason we go for back propagation. So, and this is ideally suitable for all type of problems. Now, this is a basic for you to know about the architecture that we are going to discuss right now. So, the architecture that we are going to discuss is VGGNet architecture. One second, I will take it to the slides. I'm not sharing the slide now, just 1 second, please. Yeah, now I'll share the slide. Okay, we will take the outcome from VGGNet architecture, and then we'll come back to codes that we can try with VGGNet architecture. Yeah. So if you can, I'll put it to slideshow. So this is one of the contribution that is presented in the internet from University of Oxford. So here what they are doing is like they are looking at objects, and here they are trying to see how CNN architecture can be used for analysis with respect to the objects. So here one solution that they have suggested is we can actually use DCoordinate, right, which is again part of CNN. The next that we can use is something called as cross saliency. So the advantage here is like every time we can actually be able to use these three architectures, that is DCoordinate, SciNet, and next is hybrid CellNet, which they have proposed, right? And using that, they are able to show the object saliency. They are able to show you the object saliency. Saliency actually corresponds to the changes on the objects. For example, if you see here, you have one fruit and you have a bottle next to it. So the saliency of the objects is very clearly seen using these architectures. The next what they have done is they are trying to use the same for segmenting the objects which are there in the given image. Okay. So when you look at architectures more like VGGNet and so on, you can explore for understanding the object information in the given image. Now let's go to the architectures, the next set of architecture. Okay, so the next set of architecture that we will take is AlexNet architecture. Okay. Yeah. So this is about the AlexNet architecture. As far as AlexNet architecture is concerned, it is proposed in 2012. And this architecture says that you can have 5 convolution layers, right? So as you can see here, you can have 5 set of convolution layers, and you can split it across 2 GPUs, and you can have 2 fully connected layers. And here the softmax function is used at the output layer. And this also uses stochastic gradient, right? And this says that you can have maximum of 650K 60 into 10 power 3 parameters, and then similarly you can have 630M connections. Now when you come to AlexNet, the advantage of AlexNet is like you can have long dimension images. That means that you can actually try to take a large size image and you can scale the content to a minimal dimension here. And when you come to the case of AlexNet, it uses ReLU, right, instead of tanh. So certain architectures earlier, before the AlexNet, they were using tanh activation function, but this uses ReLU here. And next, every time it normalizes output for a given input by using this formula like this. If you look at this formula here, this says very well that the inner component is based on the activity with respect to the maps that gets created. Maps here in the sense of feature maps that gets created. And the outer parameter corresponds to the mapping amplitude here, which is a to the power I xy, right? And this is that is being obtained by using AlexNet. So this again, if you look at this here, for an input image, it's equivalent output. For an input image, it's equivalent output, right? Now, if you look at this here, this is your input image. For it, it is able to find that it is a motorcycle, it's on a go-kart. So, with respect to bumper cars, what is the association, right? So, these are the results that are being presented here, just for comparison. Okay. Now, what we have seen is with respect to AlexNet architecture. Now, we will come down to the coding implementation down. Okay. Ma'am, we will have a small 10 minutes break here, and we will start by 3:30.
Yes, sir.
Yeah. So the participants also will get a little okay, and we will start by 3:30.
Otherwise, instead of giving break, we will give some interactions, sir. This is only 3 hours program.
Okay.
Program.
Fine.
We will give some question answer session to make them to be interactive.
Yeah, yeah, I'm okay.
Giving them break.
Fine. So participants, you have any questions, you can interact. You can put it in the chat box also.
We can give them hands-on, sir. Something they can try, sir.
Okay, fine. Okay, then. Okay, I will do one thing. I will now share one code which is creating from our team for data generation.
Okay.
At the time, what happens is people actually have data, and this, but when you go to research or projects, you will not have data. So I will share a code. So my request to the participants would be is to run the code and see whether the data is getting generated.
Sir, there is a question in the chat box. May I, sir?
Yeah, ma'am, please.
A question from Mr. Karthik. My question is, what is mean by filters 32 or 64? Within that 32 by 64, what has happened inside that? How it operates? Could you explain it?
Okay. Okay, I have a clarification to Karthik. Filters 32 plus 54 in context of what, sir? Actually, what is your context? Is it from some paper you are asking, or? Hello?
He has given image classification as a response. His audio is not working, so he is chatting. Image classification is working.
So, your means one way of looking at it is like ideally when you apply a filter on the image, the resultant image, right, would have a scale down, right, where the paper would have said it is of size 32 plus 64. That would be the reason actually, sir. The image that you have taken, right, would have been downsized with a size of 32 cross 64.
I think he wants to know the clarification about what do you mean by 32 filters and 64 filters for breast mammogram images, sir.
Okay, fine. So, fine. Okay. I'll just say 1 second. Just show you.
So filters are basically fine-tune the images. If you keep on doing 32 filters, your result will be absolutely good. When you go with 64, automatically it improves the performance.
Actually, what we take as it is like this. You are actually trying to take features now, sir. Karthik sir, it is like this. You are trying to take mammographic. I'm talking from mammographic images, right? I think you will be looking at probably breast cancer detection like that. So if you look at mammographic images, what we will do is like we will try to take dimension of probably at multi-factor dimensions, right? So that case, every time your features are going to be fused. So you will fuse features at 16, 32, 48, 64, 80 and so on. So if you fuse the features, right, at 32, what you got, and if you fuse the features at 64, what you got, and if you have created and resultant image, then the image representation would be 32 cross 64. That's the answer to you, sir. Karthik sir, hope I'm clear. Hello.
Yes, sir, he has responded. Thank you. And also he has given another question from Swatika. Is it possible to work speech recognition data set using CNN?
Okay. See, as far as speech recognition is concerned, every architecture has got its purpose for presentation. A recurrent neural network would be a suitable architecture for speech recognition. Not a suitable architecture for speech recognition because CNN is an architecture for image processing, or if you have a synthetic data set where every row of data you want to put it to a respective class, there you can go for CNN.
So Swatika wants an example, sir, for that.
Okay. Wants an example. Okay, I would. Okay, like for example, if you look at speech recognition, each of it are encoded characters. Let's take I say a word apple, right? So you say it is APPLE, right? So there is a pattern that is connected from A to P, P to P, and P to L, and then L to E. So there is a remembering characteristic that would go from one letter to another letter. Only because of it, the part of the speech is very clear. So in such cases, suitable. Hope this answer is clear to you, madam.
Yes, sir.
Thank you, sir. Another question is from Karthik. Is regression methods are used for image classifications?
Okay, see, answer to you, sir. Actually, any problem is formulated as a regression problem or a classification problem. If the problem is not a regression problem, you can go to classification. That is why what people do is, if you have any data, you can actually first fix the data as a regression problem and see whether it is a linear regression or a logistic regression. If it is, you can try with single or multiple linear regression models, or if you go to logistic regression, you can try with regression. Then you can go for a classification problem. That is first point. Second point is the other way of answering to this would be is, if you look at your data, if you can use a single hypothesis to classify the data, then it is a regression problem. No, the hypothesis cannot be single. I need more than one hypothesis, then it becomes a classification problem. Sir, is it clear, sir? Any other questions?
Karthik has again asked, sir, how statistic techniques are important in machine learning? Without that, it is right to conclude my model is good or bad. not.
Statistic techniques are important for machine learning. Okay. Then what is the next question?
That it is right to conclude my model is good or not.
Okay, fine, sir. I'm looking at your question in two aspects, sir. One, if you look at statistical machine learning, okay, then you can actually assume statistical machine learning speaks about statistical features first, right? For example, if you look at a medical perspective, the doctor will say that based on the cell region dimension, I can conclude whether it is a regular cell or whether it is a cancer cell. Okay, whether it is a regular cell or cancer cell, I can conclude. It is the answer from the doctor side. Now, if you're going for statistical machine learning, it means that you are trying to build some features which are statistical features. Ma'am, am I audible? Hello?
Yes, sir, you're audible, sir.
Fine. So you're trying to bring some statistical features. Together with the regular feature that you have, regular feature means what? You talk about pixel level features or region level features or edge level features. You can have some statistical features also to decide the type of class. For example, somebody says that a person has a tumor, right? Based on the region size, the person tumor level is being classified as class 1 or class 2. Doctor will say it is normal stage or advanced stage. I'm just saying from a layman thought. So there you are trying to bring a statistical feature to the data set to improvise your type of class. So that is the importance of statistical machine learning. Now, other way of statistical machine learning would be is like when you look at your data set and you are trying to predict, you are saying that I have 70% of samples being classified as positive or 30% of samples being classified as negative. There again, you are looking at the count with respect to the positive and negative samples. Because importance of machine learning is more about how much number of samples are being classified as true positives and false positives. Then you can bring in your thought process with respect to statistical machine learning. So without statistics, no modeling, sir. And without statistics, no machine learning, no deep learning, no transfer learning also.
There is a
Sir,
question.
which
from Radha.
architecture is good? Which architecture is good for image segmentation, sir?
What type of images, ma'am?
Brain images, for example.
What, madam?
Brain images, sir. Brain images.
Okay, you're talking about medical imaging. Okay, fine. Okay, if you look at okay, fine. So in medical images, brain images, what region of images you are looking at actually? What region of images are you looking at, ma'am?
Images, sir. Brain tumor.
Okay, brain tumor images. Okay, then that case CNN is more suitable.
Sir, could you repeat again?
CNN, convolutional neural network is more suitable.
Okay, sir. Okay, thank you.
Yes, ma'am. Any other questions?
ReLU or sigmoid?
Is ReLU or sigmoid? Okay. Any other question is what is it, ma'am? Is ReLU or sigmoid or?
Yes, sir. They are asking about which one is having the more advantage. I think so. Which has more advantage? ReLU, that is activation function. Whether we are using ReLU or sigmoid.
Okay, fine. See, sigmoid is actually a linear activation function. So if your data has less number of outliers, you can go for sigmoid. If your data has more number of outliers, you can actually go to ReLU. And ReLU is actually a proprietary activation function which came up when deep learning came up. In normal neural networks, we don't have ReLU at all. And ReLU is a non-linear activation function. At this point, if somebody has a question saying that I'm hearing something like vanishing gradient problem, which speaks saying that for certain classes in the maximum or in the lower, the model does not show any classification at all. So there you can go for leaky ReLU. So we have a variant in ReLU which is called as leaky ReLU. In case you suffer with respect to problems, especially with respect to overfitting or vanishing gradient problem, you can go for leaky ReLU. Any other questions?
Thank you, sir. The next question is, can be possible to get assured QoS using deep neural networks? Can be possible to get assured QoS using deep neural networks?
Okay, I think QoS is it Q quality of service, ma'am?
Sorry, sir. They have simply abbreviated as QoS. I think.
Okay. Anyway, I see. Actually, there is not as far as any neural.
Quality of service only is meant, sir.
Okay, see, actually here there is no QoS concept. Here it is only in terms of the parameters. In deep learning, we have only two keywords. One is hyperparameters, second is parameters. If you say parameters, then that means it is all measured by the model. So example is loss. So training loss, test loss, validation loss, all that are basically measurable parameters. You can actually include all the performance metrics like accuracy, recall, all that as an example here, right? So in that context, that is equivalent to saying you are trying to measure the quality of a deep learning model. QoS is more into networking perspective. That's how you can actually look at it.
Sir, another one question from Karthik. In breast mammogram, deep CNN, pectoral muscle removal is must or not?
Sorry, that I don't have context. That depends on the breast cancer images, because now breast cancer image capturing devices have come up, right? Now jackets have come up which actually people can wear and take up data also. I don't have much input on that, sir. Maybe the doctors may be the right person to answer to your question, this question. But this problem area is becoming as a more challenging problem, because there are a lot of new scope, and a lot of people are having this type of problems. Yeah, any other question?
Sir, I'm having one question.
Please, ma'am.
This is Rekha. What is the difference between image segmentation and object detection, sir? Somebody is doing segmentation in research, but somebody is doing object detection in agricultural field. Which one is best for agricultural images, sir? Like leaf images?
Okay, fine, ma'am. I'll answer to your question, ma'am. Okay, ma'am, am I audible to you?
Yeah, sir.
Okay. See, ma'am. See, let's take you have a photo of yourself. I think you can visualize now. You have a photo of yourself, your passport size photo. Is it okay? Now, now you are in some background. Your background is, let's take, that is a plain green color background, right? And what I want is like I want to actually take your photo to a new foreground and a new background, right? So there what I'm doing is I'm doing segmentation. Fine. Now when I'm doing segmentation, what happens is it actually shows the different regions of your face, which would be your hair, eye regions, and so on. And every region will be segmented, and then it becomes regions 1, 2, 3, 4, 5, which becomes a regions on the new image. Am I clear, ma'am? So the
Yes, sir.
output of segmentation would be a detection, which can be an object. Yes, sure. The Atlas of India, you segmentation at different regions. Region 1, 2, 3. Now, if you take with respect to the agricultural problem that you're talking about, can you explain the use that you have been?
Sir?
Madam, am I clear?
Sir, you are not
Your voice
audible,
is
sir.
not audible clearly, sir.
Madam, am I audible?
Yeah, now it's clear.
No, sir, your audio is not clear, sir.
Background sound from here, actually. Hello.
Sir, your voice is like echoing, sir. Your voice is echoing.
about others actually? Is my voice clear?
Yes, sir.
At present it is okay.
There's a noise and audio connection, ma'am, I think for everybody.
It's the background voice noise only coming, sir.
Okay, madam, now is it clear?
Yeah, little bit, sir.
Okay, see, answer to Rekha ma'am is, see, first ma'am, the segmentation will result in detection. Only when you segment a region or edge or pixel from the given image, you will be able to detect the objects. So detection can be object or detection can be regions also. For example, if you take your agriculture, when you are trying to apply edge detection, right? What you are trying to do is you are trying to apply a segmentation algorithm. As a result of segmentation algorithm, you will be able to detect the different objects. The objects can be the plants in the given image. So that's the answer to you, ma'am. Rekha ma'am, now is it?
Okay, so segmentation is used for segregating the portions, exactly the portions, right, sir?
Correct. Result of segmentation can give you objects.
Okay, sir, understood, sir. Thank you for your answer, sir.
Yeah, thank you.
Yes, sir.
Sir, one more question. While considering many models like UNet model, dense model, RES model, which model is suited for image segmentation, sir?
Okay, fine. See, UNet is more suitable for medical imaging. Okay, for all the information. And the UNet is more suitable for segmentation. For example, from my team, we have looked at the UNet for medical image problem. And the same UNet, we are looking at one of the problem that we are working with ISRO team. The problem is something like if you have the aerial images and if you want to segment the regions would be like the road, trees, the huts, right, on the road regions. We are trying to use UNet. UNet is giving excellent results. So UNet is more suitable for segmentation. From my experience, my limited knowledge, I am saying UNet is more suitable.
So now many of the papers are written with the hybrid model also, no, sir? So for example, they are conducted with the corner net approach with the dense net and all. So by having that hybrid models also, they are proceeding, they are giving good results. So which one will be the good one, sir? Is there any procedure or any protocol to go with the hybrid models?
Okay. See, when you say hybrid, then it differs from one more called as cascading. Right, we have cascaded architecture, we have hybrid architecture. When you say cascaded architecture, it means combination of one or more architectures together to improve the performance, right? When you look at hybrid model, then it means that you are trying to improvise the existing architecture with some sort of added features is called as a hybrid. For example, a denoising layer that is added to a deep learning is a hybrid architecture, right? So if you feel that your model data that you work has got a lot of noise and you need to work on some sort of denoising there and you are trying to add one or more denoising layers there, that's a good contribution which you can call as a hybrid model. So the nature of data will suggest you whether you can go for a cascaded architecture or a hybrid model.
Thank you, sir. Thank you.
Yeah, thank you, ma'am. Okay, I think we got enough questions, so we'll move on to the concepts. Okay, I think I should get screen sharing option now. Yeah. Okay. Yeah, fine. Thank you. Okay, now let's look at the architectures which are more popular nowadays, right? And as far as these architectures are concerned, the inference on these architectures is, and the major inferences, all these architectures have improved with respect to back propagation, right? That's only difference here. And these architectures are proprietary also because they have been introduced by some third-party communities. For example, Google has its own architecture also, right? So we will share the screen and start the discussion. Okay. So we will start with the architectures here. Okay. So you know this ImageNet architecture, which is more popular architecture with respect to object recognition. Once again, I'm having difficulty in. Once again. Just give me 2 minutes, I'm opening the slide again. Please wait, my system is getting up. Yeah, it's come up once again, sharing the screen. Yeah, now I'll share the screen. Okay. As far as AlexNet is concerned, it goes back to the paper which was based on ImageNet classification in 2012 by Alex Kilsky. So this architecture also says that you need a high powerful computing system, so you can have a GPU, or you can actually take a Google Colab and you can try to run through a GPU code also, right? And as we told you, the number of parameters is very high in the case of AlexNet. Okay, so the problem that they worked in the paper was basically the annual Olympics problem with respect to computer vision, right? They were trying to use the data set and they were trying to see what was the possible lowest error with which they were able to do the detection, localization, and classification. So this was an input later. So later they were able to conclude that across architectures, AlexNet was able to have good results on the ImageNet problem. Now the input about AlexNet architecture is, the architecture is like this. It has a convolution, it has a max pool, then you have normalization, then you have another convolution, max pool, then a normalization, then 3 convolution layers, then you have a max pool, then you have fully connected layers here. So the numbering would go like this. So this is 1, that is convolution 1, convolution 2, 3, 4, 5, you have 3 fully connected, so it is 6, 7 and 8. So the input that you provide, right, let's take before padding, the image size would be an even order. It is 224 cross 224, right? And this is before padding. After you do the padding, it is 227 cross 227 cross 3. So the first layer, they apply 11 cross 11 filters, right? Of order is 11 cross 11. And totally they apply 96 filters, and the style order is 4. So the output volume size, how they calculate is like what we saw for the CNN is calculated like this. The CN minus F divided by S plus 1. So here S is nothing but 4. So it is 4 plus 1 is 5. And N as such would actually correspond to this order, that is 227. And F corresponds to the number of filters, which is 11 here. So you get it as 55. So the output volume would be 55 cross 55 cross 96, right? Because you are applying 96 11 cross 11 filters. So number of parameters in this layer, it would be, it is 11 cross 11 cross 3, right? Because it is number of order here is 3 here, multiplied by 96, because you are applying 96 filters. So you totally will have 35K, that means 35,000 parameters in this layer. So that's what we discussed in the beginning itself. All these architectures like ResNet, AlexNet, all that, they have more number of parameters in the model. So this was the output that they were trying to show from the AlexNet architecture for the ImageNet problem. Okay. Now, after you do convolution 1, so now con 1 is done, right? Just now we have shown you. Convolution 1 is completed. So the output that you get from convolution 1 layer is 55, cos 55, cos 96. Now, next what you do is you give it to the second layer. The second layer is again having 3 cross 3 filters being applied at stride 2. Now, if you look at the output volume size, so the same formula, N minus F divided by S plus 1. So here, when you look at N minus F, N indicates 55, right? And the F indicates the number of filters. You have 3 cross 3 filters. So it is 3, and S is nothing but 2. So you say 2 plus 1, this becomes 27. So the output volume size is 27 cross 27 cross 96 at second convolution layer. Now the number of parameters in this layer will be this. So now if you look at the output representation for this is what happens. So the input image is 227 cross 227 cross 3 after you do the padding. So at every order, what happens is it goes through convolution. It becomes 55 cross 96. Then it goes to the max pool, right? You know what happens in max pooling? It becomes 27 cross 27. Again, we get to convolution here. That is con 2. So there is 27 cross 256. And so on. Finally, we reduced the size here. AlexNet is if you think of images, the series of images, you can apply a softmax function at the last. The only characteristic of AlexNet is this: it actually has the ReLU function and uses layers, and the amount of data augmentation is very high. Usually the principle of data augmentation is done like this. You rotate with and LexNet is 0.5 and batch size is 128. All the details are proprietary to the architecture, right? And it has an ensemble model of 7 layers CNN. AlexNet has been trained with different variants. So we are trained with CON 1, 2, 4, 5, right? And, if you want to extend AlexNet, it's better you can actually use it on a GPU system, right? It's been proved to be the best architecture on the ImageNet dataset. So we have already shown you in the previous slide, right? The comparison of AlexNet versus other architectures. AlexNet is proved to be diagram. That's what. So architecture. So that was this, which is ZFnet. I think somebody's audio. Your side.
JSLV ma'am, please mute yourself. JSLV ma'am, please mute yourself.
This is other deeper networks which are compared with respect to AlexNet, which is GoogleNet VGG architectures. Okay. This VGG architecture is also very popular with respect to most of the problems. So this calls itself as very deep convolutional networks for large-scale image recognition, and this was proposed in 2015, and this was also outcome of the competition which we have just seen, ILSVC competition. And here the number of parameters is 140 million parameters. Okay. As far as VGGNet is concerned, this is the architecture of VGGNet. You have an input, then you have 3x3 convolution, order 64, and similarly you have pooling at every stack, right? And in VGGNet, right, if you have smaller filters, then order would be like this. As you can see, 3x3 convolution filters at stride 1 and padding value to be 1. If you go to deeper network, then you can assume this VGGNet to be AlexNet architecture where you have 8 layers, right? So why are they using smaller filters, right? That is the first question somebody would ask. Why VGGNet uses smaller filters compared to other architecture? The reason is they are suggesting that stack of small order filters has same performance like high order filters. Like instead of saying I will use 7x7 convolution layer here, I can use 3x3 because they have proved that 3x3 has same set of performance as like 7x7 convolution. Right? That's first justification from the architecture developers. They are using 3x3 because it has the same performance as that of a 7x7 convolution layer. Right? And next that they say would be is like if you use few channels, right? The since here you are saying 3x3, then naturally you will say it is 3 into 3 squared c square, right? And same if you're going for 7, it is 7 square c squared. So you can get more better learning on the given data, right? So that's the other reason where they are using less number of channels in the case of this architecture, that is VGG architecture. And this is roughly a comparison if you look at the inputs, right? So if you look at your input data being provided, so the parameters, you can see what is the value of the parameters at every order. right? So here, the number of parameters that is getting estimated will increase as you move from one stack to another stack. Here you can see roughly it is 1728. Here you get 73,728. Here you get 2,94,000. This keeps increasing, right? That is why in theory we say that here saying that the number of parameters is very high compared to the other architecture like AlexNet. So the total number of parameters that is taken here is around 138 million parameters is the parameters that is being estimated here. Okay, you can just see here. Memory is estimated equivalently at every layer stack. Okay, as far as VGGNet is concerned, it doesn't use any general normalization here. And as I told you, you can always have ensembled model also of VGGNet. And training procedure is similar to what you have seen in AlexNet architecture. So now we have seen two architectures. One is AlexNet and next is VGGNet. Then VGGNet as such said that you can have deep network of layers, right? And it is very important to have deep network of layers because you will get hierarchical representation of what you see in the data. So you can, if you compare the architecture of VGGNet with AlexNet, what we have seen, you can see that at every stack you have more stack of layers being available. So that's why we say that it follows through a deep network of layers as far as VGGNet is concerned. So you can just call the VGGNet to be a deeper networks in comparison to AlexNet. GoogleNet everybody knows, right? It's also proprietary architecture with respect to the model here. And here, this architecture is more deeper than AlexNet, right? And GoogleNet says that it has got 22 layers, as you can see from the diagram, right? And the important thing of GoogleNet is it doesn't use fully connected layers. So there's no concept of fully connected layers in the case of GoogleNet. And next important thing with respect to GoogleNet is like it has an inception module. So with the inception module, it is able to stack the set of layer learnings. So the filters as such is more of a concatenated module. You can see in the stack, it's got a set of concatenation operations as like a tree model here. And next in theory, they say that the type of receptive fields is varying. So we have fixed receptive fields when you go to AlexNet. But here you got varying receptive fields of order 1 cross 1, 3 cross 3, and next is 5 cross 5. And the pooling operation that you perform here is 3 cross 3 here. And you can actually concatenate all the filter outputs, right, at the depth level. For example, at depth is equal to 1, you can concatenate all the filter outputs together. But if you compare this with previous architectures, the filter outputs cannot be concatenated together at every depth. It is not possible in the previous architectures. Then next here is like it is highly computational because at every depth we are trying to concatenate the filter outputs. Okay, so as you can see here, your convolution layer at every order, it can be concatenated together at the same depth. So this is output volume size. So at first 1 cross 1, it's equivalent to output, same 3 cross 3, at 5 cross 5, it's equivalent. So final learning that you should take from this slide would be is like, what is the total output size after you do the concatenation? So total output size would be is like this. It would be 28 cross 28, right? Multiplied by the values that you get after you do the convolution. So it is 128 is 192 plus 66 plus 256. This can be equivalently written as 28 cross 28 cross 672. What is 672 is the sum of the inner parts, that is 128 plus 96 plus 56. This is the number of convolution operations also can be calculated. So the number of convolution operations again will vary at every step. In this, if you see here, it will be 28 to 28 because already written from here it is 28 cross 28, right? Cross 128, right? Cross 1 cross 1 into 256. Okay. Same when you go to the next, this alone will vary. This will become 3 cross 3. And this will become 192. Same, next it will become 5 cross 5. So totally the number of operations that are performed is around, it's equal to this value, 28 cross 28 cross 96 into 5 into 5 into 256, which is around 854 M operations. So Google is very expensive in terms of the computation that you perform. So people generally suggest that you should have a very high scalable GPU system to perform GoogleNet. Okay. And theoretically, what they have said is like GoogleNet architecture has got solutions for handling most of the problems. Today, GoogleNet is used in most of the problems, but only thing is, to create a model, you need a very powerful computer to work. So this is a summary of operations that happens for each of the convolution layers. Okay, we will summarize here about GoogleNet. GoogleNet has got possibility to concatenate the results at every layer, at every depth. So we call it as a very more deeper network, computationally efficient. Right? Number of parameters is less compared to RxNet. Right? It does not have fully connected layers. It has an inception module. As far as GoogleNet is concerned, in summary, what we say here is lack of layers. It is Madam, I think somebody's audio is on. Them. Please check yourself. Okay.
Participants, please.
Yeah, it's more information. Please check yourself. The last one here for discussion, go to the code is ResNet architecture. As far as ResNet architecture is concerned, the outcome of the challenge where they suggested that we can have an extremely deeper network. So here the number of layers is around 152 layers, right? So generally deep neural networks are very hard to train, and deep networks suffer from two problems which we told earlier itself. One is called as a vanishing gradient problem, and next is called as exploiting gradient problem, right? So both these problems has been solved in the case of ResNet architecture. So ResNet architecture was able to have low classification error as far as the competition was there in ILS VRC 2015, right? So usual thinking is like this: when we continue stacking the deeper layers in a CNN, right, then what happens here is like there is possibility that the error will get increased at one point. That means a model will result in overfitting, right? So this was a main motivation to the ResNet. So what is like assume an optimization problem, right? There, the solution, we can actually try to skip the connections, right? That we are able to work in one layer. Can it become an activation to another layer, right? It is equal to saying that we can use the residual value at every time. So what will be this residual value? We can try to say h of x minus x. So we get some residual value there, right? Instead of saying I will just use h of x, I can say h of x minus x. So you will have a residual value, and based on that residual value, we will be able to fit the value which is f of x. So in conclusion, f of x is not dependent directly on h of x. F of x will be written as h of x minus x. So in ResNet, the first block it will come up is called as a residual block. So now participants can summarize to your learning that ResNet will have block layers. Okay, what is there in a ResNet is block layer. So first type of block that you will get is something called as a residual block. So what happens in a residual block is, if you look at this diagram, you can see here, every time you will actually have a parameter function which is evaluated as f of x plus x. Now what is this? Normally if you take plain layers, right, which you see in CNN, what is there in a CNN? You would say x given to a convolution layer, you are applying to a ReLU layer, again you might have convolution layer, what you get is h of x, right? So every time your h of x would be equal to f of x. But when you come to the case of ResNet, ResNet says that I will give you a residual block. So what is this residual block says is, it says that if you are given an input which is x, which is going through a convolution and a ReLU, and then a convolution, right? So you call this a con series. So here you will get something called as f of x, but that f of x, right, will be having an added part from x. So you will say h of x as f of x plus x. I'll again repeat, h of x will be given as f of x plus x, right? So when you write like this becomes a component of a residual part here. So rather than saying h of x, it will be written as f of x plus x here, right? So this is what happens in a residual block here. Now, why do we do this? If people have a question, why do we do this? Usually, when you look at interconnections, you can actually have inputs summed up at every layer. For example, if you say a to the L, you can say AL plus 1, AL plus 2 at every stack. Fine. So, but the other way here is, why don't you have a shortcut? Just give the input as an outcome to the output. Right. So that was a main motivation for going for a ResNet architecture. So this is your full ResNet architecture. If you look at this full ResNet architecture, you can see that it has got stack of residual blocks, right? So each residual block has two 3x3 convolution layers. You can see here, 3x3 convolution layer, 3x3 convolution layer, right? So one block has got two 3x3 convolution layers, and periodically you double the number of filters, right? And you downsample spatially using stride 2 in each dimension. So next what you do is you will have additional one convolution layer at the beginning, so that you can see it in the beginning part. You will have one additional convolution layer that will come up at every point, right? Then number of fully connected layers in the end. If you look at the fully connected layers, here you will not have any fully connected layers. So if you ask a question, is it similar to GoogleNet? Yes, GoogleNet also do not have any fully connected layers. This also will not have any fully connected layers at the end, right? Now if you look at the depth here, so they have looked at varying depth here, 34, 50, 152 like that. So this they have tried as equal to what GoogleNet was doing. That means at every depth, can we actually try to find the layer level information as an output? So they were able to conclude very clearly saying that they were able to train deeper networks. They were getting lower training errors. So this was said to be a best CNN architecture. And they were able to conclude saying that this architecture is because it has residual learning. What is this residual learning is? Just now we told you, your output, which is your h of x, would be given as f of x plus U. So this is a very popular architecture which people are using for research. And in accuracy here, this is accuracy comparison as you can see from the slides. So you can see which is having accuracy with respect to lower level accuracy and which has higher level accuracies. So in comparison, if you take ResNet here, ResNet has higher accuracy compared to GoogleNet. It has higher accuracy compared to AlexNet. But again, the defining statement here is, again, I am saying it's based on the data set, this accuracy will vary. Right? The data set that they have taken on the ImageNet, this is accuracy. But maybe you take some other data set, this accuracies will totally vary. And this is with respect to the operations. Right? So in gigabit operations, this is the operations with respect to the different architectures. And there, one type of accuracy that is taken is with respect to top one accuracy. One indicates a class label. And this comparison is with respect to the forward pass time, right? So forward pass in the sense from one stack of layer to the other stack. So what is a forward pass time? So you can see for the different architectures as it is being presented. So you can see the forward pass time to be more high with respect to BGP 16, right? You can see from the top here. And next what you see is actually the power consumption time. So the net power consumption time with respect to different architectures for the same ImageNet problem. So in summary, we have seen four architectures here. One is your AlexNet architecture, and second architecture that we have seen is VGG. GoogleNet we have to compare because it is architecture that says that we don't have a fully connected layer, and the same has been followed with respect to ResNet architecture. Okay. Any questions from the participants? Move on to the next part. Participants, any questions from their side? You can put it in the
Participants, you are having any questions, you can post it in the chat box also. No questions from the participants, sir. We shall move on.
Yeah, okay, fine. One second, I'm sharing the screen.
Sir, one question from the participant, how to select the filters?
Yeah, selection of filters is based on what you want to maximize as information from the given image. So if you look at image processing, every filter has a reason, right? You look at median filters, you look at Gaussian filters. Each filter has a reason what information they can extract from the image. So based on that, based on the nature of image that you've taken, you can actually choose a filters. Okay, if there's no questions, we'll move to the next part. One second, I'm sharing the screen.
Sir?
Yeah, 1 second, ma'am. Sharing the screen.
Sir, the same one more question from the same participant, where we can get the codes and the architecture, where we can get
Which are
the architect codes, any architecture, sir,
okay?
for trial things, where
Okay,
we can get the architecture codes and the models.
okay. Correct answer is the papers are one premier ones. The other way I will also show you now, ma'am, where people can actually see. Okay, that question I have noted, ma'am. That question I have noted. I'll answer to you. Any other questions? That's all, no, ma'am. Okay, fine. So this last one from the architecture side, from theoretically, is DenseNet. Okay, so these two keywords are very important for your comparison. One is deep networks and next is wide networks. Okay, so when you say deep networks, it means that you have more number of layers. That means from the top to bottom, the number of layers is more. So there you call it as a deep networks. And the number of nodes per layer will be less, right? But when you come to wide network, it means that from the top to bottom, the number of layers is less, but the number of nodes at every layer will be more. That is about wide network. So usually you can always say that you can have layers to be larger. Some people say layers should be smaller. But again, it depends on what you want to learn. I just now I told you, like if I want to combine the operations of convolution 1, 2, 3 at every layer, and I want to learn the data and then go to the next stack. So there it depends on what you want to learn at the data level. So there is no direct answer to say should I go for a deep network or a wide network, but you should know that there's something called as deep network, there is something called as wide networks. Right? And it is theoretically said that when the depth is more, the amount of learning is also high. That's other information to the people. Now in that line, we have something called as a dense net architecture. So we just now saw what is a block, right? Block layer concept. So similarly here, as far as dense net is concerned, it says that you can concatenate the output of a layer, right, to all the successive layers. So if I have many layers, I can concatenate the output of a layer to all the layers. What is that concatenate? Just see it from here now. If you see here, let's take this is the input, right? This is the input, and this is stack of layers. If you take the output of this layer, this is becoming an input, right, to this layer, this layer, this layer. That's a concept. So you are concatenating the output of a layer to all the successive layers. That's about dense net architecture. Now, if this is the input image, you are doing a convolution operation. What you are doing is you are giving it to a dense block. So the dense block as such, what it says is whatever you are trying to take as an output, you give it as an output to all the layers here. Then you do a convolution, then you do a pooling. Then again you do a dense block, right? So the output of every layer is given as an output to all the other successive layers. And finally you do a prediction. So in this example, we give an input as a horse, the output is a horse image that you get, right? Now, rough comparisons from papers about DenseNet versus ResNet, right? So if you look at this here, in terms of the number of parameters versus a validation error, right? The variance of DenseNet you can see here, right? Variance of ResNet you can see here. In terms of the error, validation error percentage, this is the performance with respect to ResNet, right? And this is the performance with respect to DenseNet. And visually, immediately people will say that the DenseNet error rate is low compared to the ResNet architecture. Second, again, with respect to the number of operations versus the validation error, DenseNet is better compared to the ResNet architecture. So it is immediately for us to understand that DenseNet is better compared to the case of ResNet architecture in terms of validation error, right? And again, validation error with respect to number of operations. So both in terms of parameters and number of operations, DenseNet is better compared to the ResNet architecture. Now, the next question that was asked is, how do I actually find the code, right? Okay, that I will show you. Now, ma'am, is there anything to any specific data set? Participant was.
No, sir, they have given. Rekha, ma'am, do you have any specific data set, ma'am?
Ma'am, I don't have any specific data set. I'm going to collect the data set from the agricultural universities, ma'am.
No, ma'am, I'm asking what is the domain of the problem? Is it medical image?
No. Agricultural leaf images, sir.
Okay, leaf image data set.
Yeah, sir. Yeah.
So you are
finding diseases and some nutrient deficiency disorders.
okay. So plant disease recognition, correct?
Yes,
okay.
Sir. Yes.
Yeah. Okay. 1 second. Okay, I'm just giving you options which might be useful for other people also. So now I share the screen. Usually, when you look for codes, right? Ideally, you can look for conferences which are premier in that, right? So you are able to see the screen, ma'am?
Yes, sir.
Yes, sir.
Okay, so you also type, you will get a lot of good URLs. Well, maybe my first set of URLs I'm getting is like this. From this, you can actually find codes. You can look for papers on it. Usually, papers that are published by arxiv.org, right? Okay, they will have codes which are put up on the GitHub. As much I know with my limited knowledge, if you have a paper that is published under this URL arxiv.org, right, they would have really got some codes which is put up on the GitHub. So you can search code on the GitHub on the architecture. For example, now you are looking at plant disease identification. You will have codes for the paper, or you can actually look for premier conferences, right? Okay, for example, if you are looking at conferences here, you will have conferences which are more premier every year coming up now, like computer vision conference. So if you look for top conferences in computer vision, you will get conferences on computer vision, which is CVPR, which is the most popular conference, or ICVGIP. These two are very premier conferences. If you look at these conferences, 80% that conferences papers will have quotes, right? So let's take, I go as a layman and see, okay, CVPR conference, right? Plant disease, right? So you would get a paper, right? As you can see here, papers are coming up now. Leaf spot detection like this. And again, this is a paper which is from 2020. And this paper, if it is based on CNN or any proprietary architecture that is there, usually these papers will have implementation which is put up in the GitHub also, right? So this is a way where you can source papers and source your code also. So let's take this becomes your research paper, which is very attractive, and this is close to your problem. They are looking at apple leaf disease identification. They have a code also on it. You can take that code and you can modify your code, modify the code according to the algorithm or approach you are addressing in your research. That's my suggestion. This is a very nice way to find an architecture which is being justified by in the open community as a good architecture because it is published in CVPR or ICVGA. Now, has it answered to your question?
Yeah, sir. But how can I get the code, sir?
Okay, fine. I'll say that also.
Yeah, sir. Okay.
So usual way of search, how I do is like this. When you put up a GitHub code, you are getting normal, right? So you will finally land in the GitHub code, and that code you can take as a code for working. Madam?
Sir, we can see.
So I'll put it in the chat box also. That's all. This is how I actually suggest to my PhD scholars also. Most of the problems which is taken in CUPR or ICBBGAP would have the GitHub, because they suggest to post the GitHub, right, for authentication of the results. So when we search, we'll get the code and the data set also. You can start working from there. Madam, has it answered your question?
Thank you, sir. Thank you, sir.
Yeah, thank you.
Noted, sir. Okay, thank you.
Chat box also. You also get it, you will get more nice papers also. But benchmarkers, you should actually look for papers from CUPR. Medical imaging also, my same suggestion to the people. Take CUPR, you will get benchmark data sets. So you need not go for an outside data set. If you go for an outside data set with a hospital, you'll have to get an ethical clearance from them. It will take a lot of time. Instead, you can take a CUPR, choose the data sets that they have taken. With that also, you can move your research or your project. So I think now there's some clarity with my answer. Okay. So the I want to take through is to give you an understanding with respect to the code, right? Okay. So can we see some codes to experiment all these architectures? So that's the next one. So I will take through the architecture codes. Give me 1 second. And when you do all these architectures, don't go by asking, understanding like, okay, what step 1, step 2, and step 3, and so on. Understand the strength of the architectures and understand why the architecture is suitable for the problem, and learn the architecture stack, as we told you, right? Then see how the variant of the architectures can be there. So whatever is the variant you can take, right? And once you are okay with that and the results are fine, no second thought, you can try writing the results and you can submit it to a premier conference or a journal. But last question, as people were asking, like which value should I give for the hyperparameters, right? That you should be clear about your reason why you have chosen the architecture. That you should be very clear. Okay. Most of the contents that I've taken is from the internet, and I will also put in the chat box a very other useful slide which is there for CNN. So one set of slides is my slides, which I have shared and discussed. Other set of slides, if people want to refer for any deep learning architecture, which is Premier, I put it in the chat box for your reference. Okay, 1 second. System is slow, just 2 minutes. People are working on problems related to medical imaging, especially on 3D data, 3-dimensional data. So there you can actually use 3D Doctor for comparison. If you are doing something with 3D medical imaging and you want to check your results, in the internet you can search parallelly before my system is coming up. So you will have something 3D, 3 is number, D is doctor, right? You can type 3D doctor. So there you will be able to get inputs about how to visualize the results with medical images, a 3D perspective. Happen to say that your problem is into 3D imaging in medical images, please use 3D Doctor software. and you can load the same images, see how much time it takes, then you can compare your results and see whether your results are correct or not. When you work on 3D images, our input to all the participants is like you will not work at pixels in medical imaging. You will actually work at something called as voxels. You will not have a pixels concept at all. What you have is something called as voxels in terms of medical imaging. So there, if you are looking for an algorithm for 3D imaging in medical imaging, you can look at MC algorithm, Marchand-Cubes algorithms. MC algorithm is very popular working on 3D medical images. Okay, 1 second. Minutes, my system is other problem with data sets.
By the time while loading, sir, excuse me, sir. Can you please throw light on how do they execute the huge volume of data in the open source, sir, using OLAB and other cloud environment? Audible, sir? Am I?
Ma'am,
Yeah. Am
sir
I
is
audible?
not there. Yes, ma'am. Sir is not there, ma'am.
Yeah, we'll wait. So if you have any doubts, you can put it in the chat box. As soon as the sir has joined, we will answer the questions. If you have any specific questions to be answered, please put in the chat box. I think sir system is overloaded and it is getting rebooted and he is getting back. Professor Senthil Kumar's system is restarting. Till then, if you have any queries, you can ask me. You can share your feedback also. At the end of the session, we would like to hear your feedbacks about the session. Sir has nicely brought about what is CNN. He has started very clearly with what is CNN and how the image data set, right, as a huge small matrix. And he has correctly spelled out the different types of filters available. And he has shown you the CNN architecture. And he has given the hands-on experience about how the architecture goes. Then he has nicely brought about different types of architectures, right from AlexNet, GoogleNet, VGGNet, and he has compared the various nets with a deeper layer and residual net, and how it is useful for the different types of applications. And he has nicely brought about VGGNet, AlexNet, GoogleNet with the architecture also. He has explained clearly. Then he has given you the input on ResNet, able to train, and he has mentioned that best CNN architecture, great innovation based on ResNet. We can have the good accuracy with respect to our the given problems. Then he has explained about what is all about deep versus wide networks, right? Deep, few nodes per layer for many layers. Wide means few layers with many nodes. This is what he has been explaining, many nodes per layer. So, which turns out that 3-layer can express functions that a 2-layer network would require exponential nodes. So, the power of depth of feed-forward neural networks he has spelled out. Then DenseNet versus ResNet he has explained. Then he has some of the participants have asked about plant disease architectures. And he has mentioned that websites, right, CVPR conferences, some authentic and standard conferences, you can see the code. And you can also verify the papers through which you may be able to get the output. So you can choose a data set, right? Most of the data sets are readily available in different places in the Google itself. You can make use of it for your applications. He's trying to explain about what is all about 3D medical images, how the medical data set could be downloaded, and in 2D we will spell out that as a 2D pixel. Only we have X and Y option, but in the case of 3D we have X, Y, Z. That's why it is called as voxels. So we have lot of imaging through PET, MRI, CT, everything is coming under the 3D analysis. We have to first convert into 2D and we can work on it. So we should know how the images have been extracted, right? With this,
Yeah, madam, thank you. Thank you for adding the inputs, ma'am. Senthil Kumar here. Any further questions, participants? I will share the code link for the rest of the architecture so that you can work at your place. Ma'am, any other questions from the participant side?
Sir, you can throw light on how do they manage with the huge volume of data set with their limited available infrastructure like small laptops?
Okay, madam.
So
Okay.
basically, they are using some free clouds, but it is not sufficient for them to handle large volume of images, right, sir? Can you
Yeah,
please throw light on it, sir?
Yeah, ma'am. Actually, there is one concern there. People generally have a worry about their code and their security to access. For example, I push it to the Google Colab, then there is possibility that somebody with my login also can access, and it is on the Google Colab. So one thing that you should keep very clear is like what is the time to code, what is the time to publish, right? So within 3 months you should finish your code, and within next 2 months you should submit your paper. And my request is like I say to my scholars exclusively, you should push your code as soon as possible to the GitHub, and you should have your code as an URL for the paper. In all your reference that you're putting, no, please put your GitHub URL that says that you are the first contributor to the problem. For example, I would say you like this now. Let's take I propose a new type of filter. And that filter I'm trying to push it to my code and it is working well. I should push it to the GitHub and say that in the abstract I should say that I proposed a new filter. So that is one way of claiming. And second thing is like the size of the data set. For example, if I take a medical image and try to run it on my laptop is crashing, everything is lost. My laptop is lost and my interest is also lost. If I talk about me. So what I would suggest to the people is you try to see the data set which is having smaller amount of size but has larger amount of challenges. Rather than saying that I have 1,000 data set, you try to speak and say that I have five images, but these 5 images are speaking about the problems of nature of data. That is why I told to the people that you should spend at least 15% of your research time in data collection. Sometimes people make a mistake. I know ResNet. I want to take ResNet and try the data set. Please don't do that like that. So first you study the data set, spend time on the data set. You prepare your data set very nicely saying that there are this many positive samples, there are this many negative samples, but whatever challenges are there in the data, right? It is like, you please ask a question. Why you are all looking at solving such medical imaging problems? The answer is very simple. I do not have a facility to see with my normal eye. My system can do that, right? That is the reason. You ask doctor, no, if you take why are they taking automated systems with respect to cancer analysis? They say that with the normal eye itself we can see cells which are red in color or which are having other colors, but your system should be able to go behind that red color pixels and say that it is not just a red color pixel, it is a red color pixel because there is an organ there in place. So you please look at the challenges that are there in the data set and prepare the size of data set. So my simple suggestion would be even 100 images is suitable to solve a research problem. Some people will say that I need 1,000 images. It's not 1,000 images. 100 images speaks about the nature of challenges in the data set. Please choose such type of data set. Third suggestion which I would say is now at least there are some HPC facility available with people. I think including Madras University also they have HPC facility. If you get a chance where you can access that HPC facility from your place, because HPCs you can access through internet wherever you are. If you happen to have a chance of an HPC facility which you can access, in your place you push the code to the HPC facility and you can execute and see the results. Because you cannot invest on new servers, new laptops, because one laptop close to GPU which I want to purchase is costing around 1.6 lakhs. In that I can get 3 laptops with my possibility. So that is the best way of doing things. But I'm still saying this architectures will come and go just like that. Now in the state of discussions where I'm also trying to talk, people say that what about the interest with respect to transfer learning? That is the other way. That is the other way I can give us a solution, right? Where you do not have a larger data or where you want to create data with possible challenges, use a transfer learning architecture. That is my suggestion. So one suggestion is you can push it to Google Colab. Second suggestion is have 100 sample images alone. I'm talking about medical imaging, only 100. But in that 100, try to make sure that it is 60, 20, 20. 60 for training, 20 for validation, 20 for testing. But as much challenges should come in the data set. And make your problem as a binary class problem. Because if you talk to doctors, now doctors, what they will say is, first I want to know whether the person has a disease or not. Then only I want to know about the type of disease. So you build a system for binary class problem that is nice for research. Then you go to a multi-class problem, then it is possible or not, that is in the time. Okay, this is my suggestion from my experience with the medical imaging. Actually, I have worked 2 projects with the Amrita Institute of Medical Sciences. One project is building a human atlas. Like you see small kids in school, no? When you want to show them a skull, you have a physical mold and open the skull and show, right? Similarly, we built a human atlas for the doctors, which is a visual animation one. The second one is actually a very complex project that is actually for the craniofacial department. The problem is something like if you have a person who is admitted in the hospital for a surgery, and let's take one of the jaw goes, I think people can understand, right? Left side jaw goes. Doctor immediately what they do is they use the CT scans, right? And they try to create the skull, normal skull of the same person. In that place, now what happens is one of the jaw portion is lost. The doctor immediately uses a device for finding the jaw portion. Any guess from people what is the device they use for finding the jaw size which is lost? Participants, everybody open to you. Let's see your guess. What device is used by doctor to find the jaw portion from the physical skull? Any guess, please? Let me start with scale. Any other answers? All of you have used it. All of you have used it.
Camera, sir?
No. All of you have used it in school. Any guess?
Magnifier?
No. All of you have used it in school for experiments. Which one, ma'am?
Caliper.
Yeah, perfect, ma'am. That's it. Vernier caliper. Doctors use a vernier caliper on the physical skull. Just they find out what is the portion of the jaw is lost. Then they ask to prepare a fixture for it. Then they go for the surgery. When they do the surgery, like as you see in TV, they look at the screen and they do the surgery by hand on the other side. Now, as the doctors are instructing the people with the surgery department, they try to cut out some portions. The human body is so sensitive that you can actually stretch the skin, right? Skin is stretchable. It's not all part of the body. At the thigh regions and all, the skin regions are stretchable. So the doctors, by the knowledge, they say cut this portion, cut this much portion, right? So some height and width is being given and the skin is cut and it is put to the face when they do the surgery. And the interesting thing is the skin as such, once you cut, you cannot go and put it again and say fix it. It's not possible. Cut is cut, right? So there what we do is we try to go to a 3D model. There we apply an MC algorithm, and there, as Madam was also supporting the discussion, we look at voxels, we look at an MC algorithm, and we create a 3D face. So with that input, doctor will be able to understand during the surgery that, okay, this is how the person's face is going to come up, right? So that's how medical imaging is somewhat related to me with the projects that I have done, and the software that we have delivered is built on MATLAB, and it is said to be better with the doctor's comments compared to 3D Doctor. 3D Doctor is open source doctor software, and in fact, you will be very surprised. Doctors are very good in computer graphics compared to us because their level of precision is very nice. They work more with, you won't believe, they work more with computer graphics softwares, even compared to me also. They work on Mac laptops. They do a lot of learning on the computers. Then they go to this, but it's a semi-automated learning in medical imaging. Whatever you say, doctor will not really appreciate or accept. Last, they put their common sense and say that, okay, this is right or wrong. Okay, this is an added input to the participants. So whatever you're doing, You look for a CVPR conference, look for a data set. If the data set is there, fine, done. If you don't get it, go to the doctors, right? And please see some problems which is possible, because in the research presentations I'm seeing now, there are a lot of data sets people are talking about, but it's very hard to take the data sets from the doctors. And even if you take, you cannot publish it in papers because it's sensitive data sets. Okay, so this is just a request to the research community who are working on medical imaging. So that's it from my side, ma'am. Any other questions?
Any other questions from the audience? If you have
Hello.
any questions, you can ask.
Hello.
Yes, sir. Yes, sir. Yes,
Yes,
sir.
I'm
sir.
Bhaskar.
Bhaskar, sir. You can answer.
Hello, excuse me, sir. I'm Bhaskar.
Yes, please, sir. Yes, sir.
I
Yes,
have
sir.
one more question, sir. We are
Please.
doing a PhD in research in TB disease. How to get
Okay.
data, sir? Is it possible to get data in hospitals, sir, primary?
Your data will be available in primary healthcare hospitals, no, sir?
Okay, sir.
You are looking at what type of...
In case of X-ray, CT images, compare with the images. So we detect a TB disease and it's based on a tool.
Sir, you are with Chennai, right now, sir?
Kanchipuram, sir. Kanchipuram.
Kanchipuram. What about KMC, Kiel Park Medical Hospital, sir?
Okay, sir. Okay, sir.
I think there you can get actually. But again, no, sir, the other way, which anyway I would like to add to you all is like, you when you approach a doctor, you may not get the data set, right, directly. But if you are working with some college, sir, your research, something is with some college.
Yes, sir. SCSU University, Enathur. Deemed University. I'm working in Pachabas College.
Okay, you're doing with Kanchipuram University.
Right, sir. Kanchipuram.
Okay. So you're with Chennai only, no, sir? Pachabas College, right? Am I correct? Your college is in Chennai?
I'm Kanchipuram. We have Pachabas College for men, sir. Kanchipuram.
Oh, they're also fine. Right. Sir, my suggestion is to approach Kiel Park College, but you can try to meet the dean, submit an official letter, right?
Okay, sir.
Through your research coordinator saying that you want data set. Then they will ask you to present to the doctors.
We have tried to in this GH also, sir, just to get a text data, sir. We don't have images. In case of in Chennai, we may be available, sir.
Chennai, it is there, sir. It is there.
Okay,
it is there because one of my other colleague, he was able to get. But only thing is, you will have to clear the ethical clearance in the meeting. You are under, if possible, you try to convince the doctors that they will also be part of the research publication.
Okay, sir. Okay, thank you.
That is the other way, sir.
Okay, thank you, sir.
Thank you, sir. Thank you.
Very nice, sir. Thank you, sir.
Thank you so much, sir. Thank you. Okay, I think somebody's audio is on. Please check yourself. Because everybody is at home, right? So,
any other questions from the audience? Thank you very much, sir, for your valuable and great input to deep learning research community. I think machine learning, we have started up with machine learning and you have given a very good and interesting, informative, valuable knowledge sharing to our participants. Specifically, those who are working in this domain, they can easily start up their work and they can get their results soon, sir. Thank you so much for your valuable input.
Yeah, so thank you all. And as madam was trying to say, thanks to Dr. Chitra ma'am and the entire team. So for the entire support you have been giving in encouraging me in delivering this type of sessions. And my information to the participants again would be like, I work completely on deep learning and my PhD scholars are into deep learning problems. And we are concentrating on transfer learning also. So in case you happen to get struck, and you are not able to find a code on the internet, please write me a mail. One is like, we are now publishing our works in the GitHub, especially my PhD scholars work. One scholar has already got graduated with PhD. So if I happen to be in the same problem area, no problem, I'll share you the GitHub on the private link. So you can access a code, use it and you can reproduce it for your research. And people, especially in the medical imaging domain, I think the sir who has spoken also, if you try to reach and you don't get the doctor right in place in Chennai, please reach me. I have some friends in Chennai in the medical field, because we are working on some projects. So I can also try to reach to the doctor. I can give you a reference. So through him also you can get the data set. Okay. Everything is a long time learning. And thank you. Thank you.
So
Thank
I
you.
would
Thank you, ma'am.
Any other questions, participants? Sir, shall I propose the formal vote of thanks?
Yeah, ma'am. Yes, ma'am. Yes, please. Thank you, ma'am.
Thank you, sir. It gives me immense pleasure to deliver the vote of thanks for this event to all the dignitaries assembled here. I would like to thank our UGC HRDC Center Directors, Deputy Director, and all the UG HRDC's office staffs, and who are all assembled here for their presence and make their webinar a great success. I extend my gratitude to our Honorable Chief Guest Speaker, Dr. T. Sendil Kumar, to take out time from his busy schedule to grace this occasion. Thank you so much, sir, for this interactive session and the hands-on session also. We can understand all the architectures, models, and why we are doing the filters, stride, and all such things. Thank you so much for the learning, sir. Thank you so much. I would like to thank our HOD, Dr. Tangavilu Professor, Head of the Department, University of Madras, Dr. Gopinath sir, Dr. Swarnam ma'am, and Dr. Lavanya ma'am. Our special thanks to our Dr. P.L. Chitra ma'am to organize this national webinar with full success. A special thanks to Dr. P.L. Chitra, Professor, Convener of the program, Department of Computer Science, University of Madras, for providing immense support to make the webinar successful. Last but not least, I thank the Bhavani for the technical assistance and UGC HRDC office staff to make this webinar very successful. And my heartfelt thanks to our participants for their interest and the patience listening throughout the session. Thank you so much.
thank you very much,
Participants,
sir.
please fill the feedback form also. Please fill your feedback form. It was posted in the chat box.
Okay, ma'am. Thank you. I leave from
Thank
here.
you very much for your valuable and great input to the participants. Knowledge sharing is excellent, sir. Awesome. Very nice.
Thank you.
Thank you
Thank you.
so much.
Personal
Sir
thanks.
has spent his time on the morning also with another webinar in our University of Madras. Sir has spent great time to us also effectively. Thank you so much, sir.
Thank you, ma'am. Thanks to you and thanks to Swarnam, ma'am. My personal thanks to the university. Thank you. Thank you.
Thank you.
Dear participants, the certificates will send you within 3 working days.
So we have another, University Grants Commission Human Resource Development Center, University of Madras, national webinar on data science. It will be held on 21st. I think it will be shared,
23rd,
right?
23rd.
I think Lavanya.
23rd, Wednesday.
23rd, between
Wednesday 2 to 5.
Wednesday 2 to 5, we have another session from Department of Computer Science. Organizer is Dr. B. Lavanya. Then followed by, we have another webinar on
Artificial intelligence.
Artificial intelligence by Dr. Mrs. Swarnam on
25th March.
25th March between 2 to
10 to 1. 10 to 1.
10 to 1. 10 a.m. to 1 p.m. Make use of the opportunity. You will get a great input. Surely it will help for your research career. Thank you so much.
Thank you, ma'am.
Thank you. Thank you so much. Bye.
Bye-bye. Certificates will be sent to your mail ID soon within 2 to 3 working days. Thank you all for your participation.
Thank you. Thank you, ma'am.
I would like to thank UGC HRDC for the opportunity. Also, I am happy to extend my thanks to Yegammai for comparing today's session. So I am grateful to Bhavani for his technical support, technical support, and organizing this event a successful one. Thank you all the participants for your interactive session.
Thank you, ma'am.
The recording has stopped.
Thank you, Yegammai and Bhavani, for your wonderful participation with great.
Thank you so much, ma'am.
Thank you.